我们的节目经常有我跟著名科学家的对话。世界顶尖科学家协会与今日头条帮我联系到了一位诺贝尔奖得主巴里什，他和另外2位科学家雷纳韦斯和基普索恩因为探测到引力波获得了2016年的诺贝尔物理学奖。在第4届世界顶尖科学家论坛即将召开之际，我要和巴里什教授进行一次深入的对谈。4年来，引力波科学取得了很多新进展，但大多数公众对这个领域仍然感到很神秘。下面我们就来和巴里什教授连线。So, what is the observable effects of gravitational stress in one direction and compress in the other direction?
Yeah.
So, since this effect is so small, how did you detect it?
Well, it's not too small to be able to use a precise instrument to be able to detect. So it's very small. The detections that we make are of the order of 1/1000. The distortions in space 1/1000, the size of a proton. So we are seeing. We have to be more accurate than the big, large accelerators, which accelerate around protons. So the distortion is that the instrument, which is behind me,
Yes.
sends light down the 2 arms simultaneously at the same time.
Yeah.
If there's no distortion in space-time and you made your instrument calibrated right, it comes back at the same time. And so if it comes at the same time, I can reverse one compared to the other, add them together, and they give 0 for an answer. But if a gravitational wave comes through, one arm gets slightly longer than the other by 1/1000th of the size of a proton. And the other one gets a little bit shorter because it's like the standing in front of the mirror. So one gets a little shorter, one gets a little longer. And so the time it takes for the light to go down the 2 arms is different, and they don't exactly cancel when they come back. And that's how we make the detection. That's the idea of making the detections. To do that requires a very, very precise instrument that has many technological innovations built into the instrument. But it's doable, and we can measure something that small. In fact, we're better now. We can do it somewhat smaller than that. So that's
Yes.
what we do. That's what the instrument is. And it's based on a very high power laser. That's what the L stands for in LIGO. The kind of instrument that compares how long it takes to go down the 2 sides is called an interferometer. So it's laser interferometer, and gravitational wave. And because we're observing something from space, we have observatory.
Yes.
So that's what LIGO means.
Yeah, laser interferometer gravitational observatory, such a long name. So it's short as LIGO.
Yeah, right.
I think this is a very common method to measure very small change of distance, right? Because historically there are many similar experiments.
Yeah, we didn't invent an interferometer. Interferometers are very commonly used. In fact, a physics student almost inevitably, when he takes his first or second laboratory, uses an interferometer, and they see what they call fringes. Fringes are the wavelength of the light as it comes through. And so you see a bright and dark fringe.
Yes. So I think curious people would also ask such a question. So since the space itself has changed, so why should the light feel any difference? So why should there change in the pattern of interferometry?
The distance down those 2 arms was just like standing in front of the mirror. One arm got shorter and one arm got a little longer, and then it reverses.
Yeah, but that's actually a description of normal physics. But when we are using relativistic, the distance itself is changing.
Yeah.
The space itself is changing.
Yeah. So since there's curvature of space and time, you can solve it exactly the same way, mathematically different, but you get the same answer. If you say the light, by having gravitational wave curves instead of goes straight. If it curves, it obviously takes a little longer to get there.
So the main difference between LIGO and the normal interferometer is that it's much more accurate, right? So what are the main tricks of LIGO?
The main tricks to make it accurate, one is brute force, make it big.
Yes.
Okay. So that's just costly. And so you can see it's very big. It's 4 kilometers on a side. So it doesn't fit on my little table. And instead, it's very big. That makes it cost more, of course. The second is that we need lots and lots of light so that we can see a very small effect. So we have a very powerful and very special laser that we make. The third is that the interferometer we can't allow any scattering of the light because it won't follow the path that it's supposed to follow. And so this huge volume is under very high vacuum. And lastly, there's a lot of optical tricks that we've invented that I won't describe in this short interview because they're very subtle. But altogether, each one gave us another. So if we start with a standard interferometer being being capable of seeing 1/1000th the wavelength of the light, by making it very long, we can make it 1/1,000,000th. And then we make it in vacuum, that gets another factor, and then various special so it took, they're not limited by physics, they're just limited by our brains. And so we had to invent and then try optical techniques that would make the interferometer act as if it's even longer than this, much, much longer. And that we were insensitive to any impurities and imperfections in the mirror and so forth. And so in the end, we had to be able to tell 1 part in 10 to the 12th, as I said, the wavelength of the light, and that's what we did.
Yes, that's a miracle. So I heard that you must get rid of all the known effects. For example, if a truck pass by, and you should see that it's a truck, not a gravitational wave.
Yes. So there's 2 things. There's one is all the environmental problems that just bother you. A truck driving by, an airplane flying overhead, lightning, you can invent it, but no matter, even though we go to a very remote place, there's all kinds of natural phenomena that cause effects. Then the last one is that any apparatus like this is sitting on the ground. And even though we think that the ground is very stable, it's not. It's moving very much compared to what we have to measure. Yeah. So we have to have a very special way to make the apparatus insulated from any motions in the ground. So it's basically floating above the ground. And we use 2 techniques to do that. One technique is basically the same technique that makes your ride smooth in a car. So when you drive in a car and you go over a bump, the bump in an old car, when they invented cars, you went over a bump and you go up and down. But now when you go over a bump, it's very smooth. And that's done by what are called shock absorbers. And the shock absorber is just a big spring that takes the motion and it basically dampens.
Shock absorber, right? You said
what?
Shock. What did you say? Shock absorber.
Shock absorber.
Okay.
That's those are in your cars, underneath the car, and makes your ride very smooth. And so we made the world's most sophisticated shock absorbers, much better than what's in your car. And we made 4 layers of them so that if the earth shakes, it's through 1 layer, they have to go through the second, which is independent of the first, the third, and the fourth. With all of that, we still weren't good enough. So we couldn't isolate from the earth well enough with just shock absorbers. So we added a second technique, and that technique is the same one that you're probably familiar with. If you take an airplane ride, you can put on these earphones that make it very quiet. And the way they work is they sense the noise from the engine, ambient noise from the engines of the airplane, and they cancel those, okay? Those are ambient noise, they can cancel. But when the stewardess comes and asks you if you want a cup of tea, you hear her perfectly well. So, because that's not ambient noise, it's real, it's a real signal. So we added inside this set of shock absorbers, seismometers that measured any residual motion, and then active pushing to correct for any motion that was still there. The combination of all that isolates us from the Earth so well that we could make the detections of gravitational waves.
So, and you also made this arms twice, right? In two places.
Yes. The picture that I have here, the interferometer behind me, here is in the northwest corner of the US, in the state of Washington, in a remote part of the state where it's high desert, which is what you're seeing, and that's called Hanford, Washington. The second one is in the southeast part of the US in the state of Louisiana, and it is an identical instrument, but it's in a very different part of the US, so it's in a forest. So it's inside of a forest where we basically cleared the trees to put it where it is. So we used two of them. We used two of them to make sure that what we see is gravitational waves. That we see the same thing from both, because any disturbance on the Earth won't happen in Louisiana and in Washington at the same time. It takes time to get there for any motion on the Earth. But since gravity travels at the speed of light, they happen at almost the same time. So, and by looking at precisely when the signals arrive, we can tell where it came from in the sky. We need a third one to do that. And the third one that we have is Virgo, yeah. And so with that, we can do what you do on a ship, which is triangulate to see where the source comes from.
So as far as I know, China is building some large projects on gravitational waves, so such as the ALI CPT, which is ALI Cosmic Microwave Polarization Telescope, aiming to detect a remote signal of the Big Bang, and the Taiji program and the Tianqing program, both of which intend to place gravitational detectors into space. So how do you think about these projects?
Great. I think they're wonderful science and very forward-looking. They're different from each other. So the cosmic microwave background has been I think our best way to look at the early universe. The next generation of cosmic microwave background experiments, there's a new generation being built in the US, and I hope equally in China. We'll be able to see enough about the early universe so that we might actually see the history of gravitational waves in the early universe. Gravitational waves in space is a different subject, but incredibly important. And I think we only know after we do it, but in the same way that it's been for astronomy. In astronomy, Galileo took what we saw with our naked eye and basically used a telescope and saw that Jupiter has 4 moons. And that was the beginning of modern astronomy. You couldn't see the 4 moons with your eye. And so now we made better and better instruments. But what has been revolutionary in the last 50 years in astronomy is that we look at the same phenomena, not just in visible light, but in light in different wavelengths, in the ultraviolet, in the infrared, in the X-ray, in radio waves. And we study all these different wavelengths. And it's the combination of that that has given us the ability to understand the phenomenon behind the astronomical discoveries. They call that multi-wavelength astronomy. It's very analogous for gravitational waves. We can study gravitational waves. We do it in what we call the audio band. It's what we can do on the Earth's surface. If we go in space, we do the complementary experiments of studying gravitational waves in different wavelengths, longer wavelengths than we do in LIGO. So it's making the study of gravitational waves multi-wavelength, just like we have done in astronomy. And I'm very optimistic that that'll give a tremendously new insight into what we see. There's two different proposals. I don't know where they stand in China. Maybe you can tell me. But they basically complement each other. They're different. And if either is done or both are done, it would be wonderful for science, I think. What you didn't mention already is built in China and is, I think, going to be very, very important. It's called FAST, F-A-S-T.
Yes.
It's the biggest radio telescope in the world.
Yeah.
We lost the second biggest one, which is called Arecibo. And so China has the wonderful opportunity of having built an enormous radio telescope, which I think will also be extremely important.
Thank you. So as far as I know, the difference between TIDE program and Tianjin program is that one is putting the detectors surrounding the Earth, and the other is putting the detectors surrounding the sun.
The one around the sun, of course, is more ambitious, and that is the way that there's an equivalent space experiment being put up by the European Space Agency in collaboration with NASA. And it's in that orbit. The other one will be sooner, and I think is also worth doing. Not as ambitious as putting it that far out, but also very, very important.
Thank you so much. So thank you very much for accepting our interview.
Okay, well, thank you.